Hello.
Yes,
Now we do about Biot-Savart's law. We do
by Roberts.
Biot-Savart's law. What is Biot-Savart law? Okay. Biot-Savart law. Biot name of one scientist and Savart is another scientist. As per this law, suppose there is a current carrying conductor. There is a current carrying conductor. This is one conductor. Okay. Through this conductor, suppose I current is passing. What is the current through this conductor?
I.
I. Whenever current is passing through a conductor, around the conductor there is a magnetic field.
Yes, sir.
Whenever current is passing through a conductor, magnetic field produced by that current. So now, in this conductor, we take one small element. Suppose this is element. Element means we take very small length of this conductor, dl. And through this conductor, through this element, the current is I. Now, from this element, at some distance r, from this element, and at some distance r, you consider one point P. P is a point at a distance r from the element. Now this line, the line joining from element to point P, this line makes an angle, some angle theta. Makes an angle theta. So theta is angle between dl bar and r bar, where r bar is the position vector. Position vector means you can say the distance from the element to point P, the line.
Yes,
So
sir.
now this element of length L, element of length dl, this element makes an angle theta with the line joining from element to point P. Now what is the magnetic field at point P due to the element? Current element dl. Okay, current element. Current element. Current element means you can write it as current I and dl. dl is the length of the element. IDL. Alright. So now this element means a small part of this conductor. Small part of this conductor produce magnetic field at P. So as per Biot-Savart law, the magnetic field, the magnetic field, the magnetic field, that is why I am writing as a dB, and a very small magnetic field produced by small element. The magnetic field produced by the magnetic field produced by an element dl, an element dl, an element dl produces an element dl at p, at a distance r, at p, at point p, at point p is db, is db, is db proportional to I, and the current, the magnetic field at point P directly proportional to current. More the current through element, more the magnetic field. And also it is directly proportional to dl, length of the element. More the length of element, more the magnetic field. And also it is directly proportional to sine theta, where theta is angle between the direction of dl and the direction of r bar. And it is inversely proportional to square of distance. This is Biot-Savart law. So according to Biot-Savart law, the magnetic field produced by an element is dB directly proportional to I, directly proportional to dl, directly proportional to sine theta, and inversely proportional to square of the distance. Okay.
Yes, sir.
Now, if you combine all these points, you get dV proportional to I dl sine theta by r square. That means dB is equal to some constant, proportionality constant, that here it is mu naught by 4 pi, I dl sine theta by r square. So, with the help of Biot-Savart Law, we can calculate what is the magnetic field at a given point by a current element. Current element means a small part of the conductor through which current is passing. dB is equal to mu naught by 4 pi ideal sine theta by r square. And dB is a vector quantity. Magnetic field is a vector quantity here. So how to find the direction? So we have to write this in vector form. Direction of dB in vector form, we will write like this: dB bar is equal to mu naught by 4 pi I dl bar cross r bar cross product dl bar cross r bar by r cube in vector form. You know dl bar cross r bar is dl r sine theta. dl bar cross r bar is dl r sine theta. You know a bar cross b bar is ab sine theta. dl bar cross r bar is dl r sine theta. So in the denominator, if you write r cube, one r get cancelled in the numerator, one r. So you will get finally mu naught by 4 pi ideal sine theta by r square. Now what is the direction of dB here? Important. How to decide direction of dB? You can decide direction of dB by right hand palm rule. And you keep thumb in the direction of current. And fingers, right hand palm fingers along the direction of R bar. Then if you fold,
Anti-clockwise. It's anti-clockwise.
yes, and magnetic lines are anti-clockwise. But how do you get the direction of magnetic field at a given point? You have to draw tangent there.
Yes, sir.
If you draw tangent to that circle at P, how that tangent will come? Tangent will come into the board. It go into the board here.
Yes, sir.
This is a dB. So direction of dB is into the board on right side of this element. If you take point P on the left side of this element, then direction of magnetic field is away from the screen, away from the board. You got it, I think?
Yes, sir.
And the direction of dB is perpendicular to the plane containing dl bar and r bar. dl bar and r bar in one plane. Then direction of dB is perpendicular to that plane.
Yes, sir.
Direction of dB. For example, if right hand thumb you have to keep in the direction of current. Right hand thumb in the direction of current. Then fingers of that right hand. Okay,
Yes, sir.
you have to keep in the direction of this one, like yes, like this. Right hand thumb is in the direction of current. Thumb is in the direction of current. Thumb in the direction of current. Thumb we have to keep in the direction of current. Then this fingers in the direction of magnetic field.
Yes, sir.
Right hand thumb in the direction of this fingers are in the direction of r bar. Fingers are in the direction of r bar. R bar is along this side. R bar. This is R bar. Then you give a push and you fold the fingers. If you fold the fingers, fingers will go inside now. Fingers will go inside. So their magnetic field is into the plane. Into the plane. Alright? And this is a theta. This is the angle between theta. This is the theta.
Yes, sir.
Okay. Okay. So what is Biot-Savart law? Tell me, with the help of Biot-Savart law, what do you calculate? With the help of Biot-Savart law, what do you calculate? You can calculate
The
these.
magnetic
Hmm.
field at a point P produced by an element dl.
Yes. Magnetic field produced by a current element mu naught by 4 pi ideal sin theta by r square. And here mu naught is called permeability. Mu naught is called permeability of medium around the element. Here I am writing mu naught means we are assuming that there is a vacuum around the conductor. We are assuming that there is a vacuum around the conductor. So mu naught is the permeability. Mu naught is called permeability. Mu naught is called permeability. So magnetic field dB is equal to mu naught by 4 pi I dl sin theta by r square. Here mu naught is permeability of vacuum. Permeability, permeability of vacuum. And we assume that there is a vacuum around the conductor. We assume that, and we assume that there is a vacuum around the conductor. There is vacuum. There is a vacuum around the conductor. There is vacuum around the conductor. If there is some other medium, you have to write permeability of that medium. And value of mu naught. Value of mu naught is 4 pi into 10 to the power of minus 7. Value of mu naught is 4 pi into 10 to the power of minus
My
7. Its unit is a Tesla meter by ampere. Tesla meter by ampere. Okay. So Biot-Savart law. With the help of Biot-Savart law, we can calculate magnetic field produced by a small current element. Okay, and direction of dB is perpendicular to the plane containing both dl bar and r bar. Suppose in a conductor children, suppose current is going up. If current is going up, now at this point magnetic field is into, and if this side if you take magnetic field is away, dB inside here, this side dB is out of the plane. Suppose current is going down. Suppose current is going down like this. Current is going down. Now tell me what is the magnetic field on the right side?
sir, on the right side will be inside and left side will be outside.
On the right side it is
Uh, so
on
on
the
the right side will be outside, left side
ah,
side
on the right side it is out. On the left side it is into the
inside.
plane. Is it okay?
Yes, sir.
You keep thumb in the direction of current and put the fingers. Okay.
Yes,
Now
sir.
now if current conductor is like this. Now tell me what is the magnetic field here? If current is going towards right side, then keep the thumb in the direction of your right hand palm. Right hand palm,
So,
thumb in the direction of current. Then fold the fingers. When you fold the fingers, fingers come
so
away
it
from,
will be outside.
they come away outside. This side, magnetic field is into the board. Is it okay or not?
Yes, sir.
Magnetic field. I hope you are following.
Yes, sir.
Okay. Here it is away. Here it is away. Viva. Here it is into the pole. Am I correct? Will you be able to decide?
Yes, sir.
Okay, right. If current is like this, for example, current is going like this, then what is the magnetic field direction here?
So it will be inside.
Inside. It will be inside dB. This side it will be
So inside means you should write
inside. Sorry, that is inside. Yeah, inside. This is inside. Here it is outside. Okay, this is inside, and here it is outside. All right.
yes, sir.
Okay, right. So now, using Biot-Savart law, we derive an expression for magnetic field due to magnetic field on the axis of a circular coil. Is it okay?
Yes, sir.
Now what we do in the examination, they ask important question. Important question only. This is important. Using Biot-Savart law. Using Biot-Savart law. Using Biot-Savart law. Derive an expression for magnetic field at a point on the axis of a circular plane. Using Biot-Savart law, derive an expression for magnetic field at a point on the axis of a circular current carrying coil. At a point on the axis of current carrying loop, circular current carrying loop. Understood? This
Yes,
is
sir.
using Biot-Savart law. Derive an expression for magnetic field at a point on the axis of a current carrying loop. Okay, now we take one loop. For example, you say uh, like this. This is one plane surface like this. Yes, one plane surface. In this plane surface, there is one coil like this. There is a coil. There is a coil, circular coil. There is a circular coil in this plane. There is a circular coil in this plane, like this circular coil. Okay, circular loop. In this loop, current is passing. In this loop, suppose some current is passing through this loop. In this loop, some current is passing here. In this loop, some current is passing here. Let that current you say I. I is the current through this loop.
Yes, sir.
I is the current. Now, from center of this loop, you draw one line perpendicular to plane of this loop. This is called axis. This is called axis of the loop. Axis. Now, on this axis, we take one point P. One point P here. Now, this point is at a distance x from center of the loop. Center of the loop O. From O to P, this point P. This you say x distance. Now, this loop, we divide into small parts. We divide it into small segments. DL, DL, DL. So we take one DL on the top. I take one DL on the top here, this one. If I take one DL on the top, this is a DL. This is our DL. And from this DL, join to this point on the axis. From this DL, join to this point on the axis. Followed?
Yes, sir.
Now this DL element, this DL, this DL element current is like this. Current is going like this. And then now this current makes 90 degrees with this line. This current makes 90 degrees with this line. Yes, this is a line joining from element to point P. This is 90 degrees here. This is 90. Wait. Okay, 90 degrees. This is 90 degrees.
Yes, sir.
And this is the element DL. This is one element DL. Now, here, this is what this distance is root of r square plus x square. This is r square plus x square, where r is the radius of this loop. R is the radius of this loop. R is the radius. This r is the radius of the loop. All right.
Yes, sir.
Now, at point P, we find what is the magnetic field here. At point P, as we apply Biot-Savart Law, and we tell what is the magnetic field at this point P. What is the magnetic field at point P due to 1 dl? What is Biot-Savart Law? Mu naught by 4 pi I dl sin theta by,
I square plus a square whole to the power of 3 by 2.
yes, why 3 by 2? No, what is the magnetic
Sorry,
field?
sir, I got confused.
Mu naught by 4 pi, and this magnetic field at this point is perpendicular to this line, like it is perpendicular to this line. This is a dB, and it is at 90 degrees to this line. So this is your dB. So what is the dB due to one element on the top of this loop? One element on the top. dB is equal to mu naught by 4 pi I dl sin theta. Theta 90 here. Angle between direction of dl and the direction of the line. I hope you are
Yes, sir.
getting my point, I think.
Yes, sir.
Is it? So
Yes, sir.
here, this is a current is coming along this side. DL bar and line is 90 degrees here. 90 degrees. Therefore, what is the dB? Magnetic field due to one element on the top. Magnetic field. Magnetic field due to magnetic field due to one element. Magnetic field due to one element. One element on the top of the loop. One element on the top of the loop.
Mu
On the
naught by 4 pi of
one
I
element
dl
on
sin
the,
theta by r square.
yeah, one element on the top of the loop is, what is magnetic field on the one element on the top of the loop? dB is equal to mu naught by 4 pi
I dl sin theta by
I
r square.
dl sin 90
Theta.
here.
Yes, sir.
Angle between dl and line is 90. Ideal sin 90 by root of r square plus x square whole square. I hope you are getting this point. Root of r
Yes, sir.
square plus x square whole square. Now this you will get dB is equal to mu naught by 4 pi I dl by r square plus x square. This is sin 90 is 1.
Yes,
Similarly, now what we do, we resolve this dB into two components. And suppose this angle I am taking as a phi. This angle is phi. Then this is a dB cos phi. This side, now if we resolve this one, this side the component is dB sin phi. This is dB cos. Sorry, this angle is also phi. If this is phi, this angle is also phi, then this is dB cos phi, dB cos phi, and this side, this component is dB sin phi. And we resolve dB into two components. Similarly, I take one more element diametrically opposite to the first element. I take one more element diametrically opposite to this here. I take one more element here, and from this element I join a line. I join a line, and this is the element here. This is the element DL. Join from this DL element to this point. Yes. Join this DL element to this point. Now here also this is again 90 degrees with this line. DL makes 90 degrees with the line root of r square plus x square. Now due to this DL also there is a magnetic field. This magnetic field again perpendicular to this line, and it is 90 degrees. This is 90 degrees. Now resolve this dV into again two components. If we resolve this dV into two components, one component along the axis, this is dB sin phi. The other component is dB cos phi, this side. dB cos phi.
Yes, sir.
dB sin phi, dB cos phi. Okay. Now,
Yes, sir.
now this is also phi. By symmetry, this is also phi. So then this is phi, dB cos phi, dB sin phi. Now if you observe the figure, dB cos phi components are equal and opposite direction, they get cancelled out. dB cos phi components, the components dB cos phi, they are perpendicular to axis and they are equal and opposite direction, they get cancelled out. Whereas the components dB sin phi, they are in the along the axis. So we have to add them. Now we took two elements. One element DL on the top of the loop, another element DL at the bottom, diametrically opposite to it. So due to two elements, we are getting 2 dB sin phi. Similarly, we can divide the whole loop into very small segments DL. So due to every element DL, you get 1 dB sin phi along the axis. So to get the total magnetic field, you have to summate all the dB sin phi. dB cos phi, they are getting cancelled out. Whereas dB sin phi components are along the same direction, you have to add them. So to obtain total magnetic field on the axis, you have to add all the dB sin phi. Therefore, the total magnetic field at P, therefore, total magnetic field at point on the axis, total magnetic field at a point on the axis, B is equal to integration of dB sin phi, This you take it as equation 2, and this you take it as this one, you take it as equation 1. Now, from figure, sin phi is equal to, from figure sin phi is equal to, tell me what is sin phi from figure? From figure, sin phi is how much? Opposite side by hypotenuse. What is the opposite side to phi? R. Sin phi is equal to R by sin phi is equal to R by root of R square plus X square. Opposite side by hypotenuse. Following? Hello?
Yes, sir.
Sin phi. Opposite side by hypotenuse, like this. This is the circular loop, and this is the axis, and here we took an element. From here we join here, and this is the radius. Now this is 90 degrees here. and this is a root of r square plus x square. This is a phi. So sin phi is equal to r by r by root of tell me sin phi is equal to r by root of r square plus x square.
X1.
This you take it as equation 3. This you take it as another equation. This you say 3. This you say 3. Now what we have to do? We have to substitute 1 and 3 in 2. We have to substitute 1 and 3 in 2. Is it?
Yes,
We
sir.
have to substitute 1 and 3 in 2. Wait. I'll write this here. Wait, please. It won't appear.
Sir, once can you say, okay, nothing, sir.
Wait. I'll write again here. Here, this is dB is equal to this one. dB is equal to, I'll write here. dB is equal to mu naught by 4 pi, mu naught by 4 pi, I dl by root of r square plus x square. No root will go out. Root will go out. Sorry, root won't be there. IDL by r square plus x square. R square plus x square. This is equation 1. Now, total magnetic field at point on the axis is equal to total magnetic field at point on the axis is equal to, I'll write this one here. Please write. Total magnetic field, and you have to integrate all dB sin phi. So then total field at P is equal to total magnetic field at P at point on the axis, at point on the axis, total at point on the axis B is equal to, you have to do integration of dB sin phi, integration of dB sin phi, and from figure sin phi is equal to r by root of r square plus x square. Is it okay? Now if you substitute 1 and 3 into, this is 2, equation 2. If you substitute 1 and 3 in 2, this is your 2, equation
Yes, sir.
2. If you substitute 1 and 3 in 2 equation. In 2 equation dB B is equal to, in 2 equation B is equal to integration of dB sin phi. dB sin phi. This is equation 2. Now if you substitute in this equation, B is equal to integration of dB means mu naught by 4 pi I dl by r square plus x square. This is your dB. And sin phi is opposite side, r by root of r square plus x square. This you will get. And this if you simplify further, this you will get mu naught by 4 pi I dl into r by r square plus x square power 3 by 2 you will get. 3 by 2. This is the integration of this one. This you can write it as mu naught by 4 pi I dl. Dl will write in the integration I into r, mu naught by 4 pi I into r by r square plus x square power 3 by 2 into integration of dl, because these are all constants, mu naught 4 pi I r x, these are all constants. So
Yes.
integration of dl is 2 pi r. If you add all dls, you get the total length of this loop. If you add
Okay.
all dls, and the integration of dl is 2 pi r. So this you will get mu naught by 4 pi, I r by r square plus x square power 3 by 2. Integration of dl is 2 pi r. And if you say on simplifying this, you will get mu naught 2 pi will go 2 times in the 4 pi. 2 pi will go here. This 2 pi will go 2 times. And you will get mu naught I r square by 2 into r square plus x square power 3 by 2. B is equal to mu naught I r square, by, is it 2
Yes.
into, wait, I write it below. B is equal to, B is equal to, therefore B is equal to mu naught I r square by 2 into r square plus x square power 3 by 2. This is the final formula for magnetic field on the axis of a circular loop. Mu naught I r square by 2 into r square plus x square power 3 by 2. And if there are n number of turns in the coil, this is for only one loop. If there are n number of turns in the coil, then you have to multiply this with n.
Yes.
Okay. So up to this you have to learn. This is the derivation for magnetic field at a point on the axis of a circular loop. If there are n number of loops in the coil, if n is equal to number of loops, number of turns, in the coil, in the circular coil, then magnetic field on the axis of the coil, magnetic field at a point on the axis is equal to mu naught n I r square by 2 into r square plus x square power 3 by 2. This is. And if you put x0, x is the distance from center of the coil to the point on the axis. Here x is the distance from center of the, you see, x is the distance from center of the loop to the point on the axis x. So if you put x0 here, you get magnetic field at the center. At center of the coil, x is equal to 0. Therefore, magnetic field at the center of the coil, is mu naught n I r square by, if you put x0, then it becomes in the denominator 2 into r square power 3 by 2. R square power 3 by 2 means r, no, at the center of 2r cube you will get. If you put x0, it is 2r cube. 1r will get cancelled out, r square get cancelled out. Therefore, magnetic field at the center of the coil is equal to mu naught n I by 2r. This is the magnetic field at the center of circular current carrying coil. Is it? And also here is see, if current in the loop, this is the one plane surface like this. Here it is going, current is going like this. If current is going in this way, here magnetic field is along this side. Here magnetic field is B along this side. If current is in ulta direction, for example, if current is in the plane, in the plane, if current is going like this, if current is going in the loop like this, and in this way, if current in the loop is in this direction, now here magnetic field at the center, magnetic field on the axis, here magnetic field is in this direction, V bar. Understood? How the current appears from right side? Hello? If you see the current, direction of current, how the current appears here, how the direction of current appears if you see from here, if you see from here how the direction of current appears, tell me. And in this case, how the direction of current appears here, in this case here, if you see,
Sir, from
no,
in
is
the
it
above,
clockwise or anti-clockwise? That you have to tell me. If you see from,
in the above case, it's anti-clockwise. In the
yeah,
below
direction
case,
of current
it's clockwise.
anti-clockwise, direction of current, direction of current, direction of current anti-clockwise, direction of current anti-clockwise, anti-clockwise. Uh, Here in the below figure here, direction of current is clockwise. For if you see direction of current clockwise, direction of current clockwise. Correct. This appeal won't wait. I'll draw this figure somewhere else because it won't visible there. Wait. Yes. If direction of current is clockwise, anti-clockwise, anti-clockwise అంటే that side of coil behaves like a north pole. North pole. Okay. I draw diagram. Okay.
Yes, sir.
Like this. This is the axis. Now here magnetic field is this side. Here it is clockwise. If you see the current, current is clockwise. If you see from here, if you see from here, current is clockwise. Current clockwise. Okay. If current is clockwise, you fold your fingers, right hand palm fingers fold in the direction of current. Thumb is coming which side? In the first figure.
Mm.
In the first figure, right hand palm. In the first figure,
So it's going towards right side.
right side. And thumb is and magnetic field is towards right side. In the second figure, fold your right hand palm in the direction of clockwise direction, then thumb will go into the left side.
Yes, sir.
Okay. And with the help of direction of current, you can tell what is the direction of magnetic field.
Yes, sir.
Now, what is the finally formula for magnetic field on the axis of a coil? What is the magnetic field on the axis of a coil? Mu naught Ni r square by 2 into r square plus x square power 3 by 2. What is the magnetic field at the center of the coil?
So it's Ni by 2.
What is the N?
Number of
N is the number of turns in the
The coil.
coil. If there are 50 turns, sometimes a coil made with 50 turnings, then you have to write N50. If they say number of turns in the coil is 100, then you have to write N100.
Yes, sir.
Okay? Uh, this is, we want to take screenshot or we will take afterwards.
Once can you go to previous slide, sir?
Wait, before that, let me complete one more, then we will do. Okay?
Yes, sir.
Uh, Before that, this is also important. Hello, this is also important. That is magnetic moment of a coil. Magnetic moment of a coil. Magnetic moment of a coil. Magnetic moment of a coil denoted by letter M. It is a vector quantity. The way electric dipole moment, here also there is a magnetic dipole moment of a coil or simply magnetic moment.
Yes, sir.
Now, the electric dipole moment in electric field, in electrostatics, we did about electric field on the axis of a dipole. Suppose there is a dipole minus q and plus q. This is a dipole. On the dipole, axis of the dipole, axis means the line passing through joining the two charges. Now, at a given point on the axis, what is the electric field on the axis of a dipole? E axis. We get a formula electric field on from center to this point is you say R and A 2A is length of the dipole. Then electric field on the axis of a dipole for a short dipole E axis for a short dipole for a short dipole. Short dipole means length of dipole is negligible compared to distance R. For short dipole
2p by k
R
2p by r
Yes,
cube.
for a short dipole, electric field on the axis is equal to 1 by 4 pi epsilon naught 2p by r cube. 1 by 4 pi epsilon naught 2p by
R cube.
r cube. Here also, just now we derived expression for magnetic field on the axis. P axis is equal to mu naught n I r square by 2 into r square plus x square whole power 3 by 2. This we got. Now here for a short coil, ante if size of coil is very small, ante if R is very less than X, ante R is a radius of coil is very small, radius is very small compared to the distance X. This is X and radius is very small. Radius R is very small. If R is very less than X, if R is very less than X, then magnetic field on the axis. If R is very less than X, you can neglect X square. Then you will get magnetic field on the axis of a circular coil. B axis is equal to mu naught n I r square by 2x cube you will get 2x cube, and this you can write it as B axis is equal to mu naught by 4 pi mu naught by 4 pi into 2 into ni into pi r square by x cube we can write. Same, this and this are same only. This and this are same only. Mu naught by 4 pi 2 ni pi r square by x cube. Is it? Any doubt? Okay, same. Now this you can write here. Pi r square means area of the coil. Pi r square is nothing but area of the coil. Area of the coil A. So we write pi r square plus my A. Then you will get magnetic field on the axis of a circular loop is equal to mu naught by 4 pi 2 n I A, where A is area of the coil by x cube. This NIA is called magnetic moment. The product NIA It is called magnetic moment. So this we can write it as B axis is equal to, from here, B axis, magnetic field on the axis is equal to mu naught by 4 pi into 2m by x cube, 2m by x cube. Now it is similar to magnetic field like electric field on the axis of a dipole. There you got 1 by 4 pi epsilon naught 2p by r cube. Here you are getting 1 mu naught by 4 pi 2m by x cube. Here m is called magnetic moment, where m is equal to NIA. Therefore, magnetic moment of the coil. Therefore, important, magnetic moment of a coil. Therefore, magnetic moment of a coil. Magnetic moment of a coil. M is equal to NIA. This is very important. Magnetic moment of a coil. M is equal to NIA. N is number of turns. A is area of the coil. I is current passing through the coil. M is equal to NIA. N is the number of turns, no unit. I is ampere current, and A is area meter square. Magnetic moment of a coil. M is equal to NIA. N is number of turns in the coil. As number has no unit, so N has no unit here. So I is ampere. I is a current. Unit of I is ampere, and A is area of the coil. Its unit is meter square. Therefore, unit of magnetic moment, unit of magnetic moment is equal to ampere meter square. Ampere meter square. Ampere meter square.